Okay. What do you guys want to talk about today? Snow?
Yeah, that was fun.
We got like 18 inches. Yay.
You did?
Yeah.
Where do you live?
Mount Hood.
Oh, Jesus. Yeah, that's a lot. 18 inches. Yeah, in the snow. Woo. Yeah.
Plowed, plowed twice.
My husband said he's glad he's not pedaling in that because he rides his fat tire bike from our house to work. It's like a mile and a half, 2 miles.
What bike does he have? Because I have a salsa buck saw.
No, he's
It's a specialized fat boy.
That's the first one I had, and so I had that bike. And then when salsa came out with the buck saw, I'm like, oh my god, it's full suspension. I gotta have it. It's great. I mean, I love the Fat Boy. I'm still running those rims and that front tire, but um, the full suspension is super nice.
Yeah, this particular bike is literally just to get me to and from work. So I was like, I don't need a full suspension bike. I
Sure.
actually either tomorrow or Friday have the 2020 Specialized Enduro coming to my house, so I'm super pumped about that.
Yeah, that'll be a lot of fun.
Yeah, for sure.
But yeah, the Fat Boy is great for this kind of weather.
Yeah.
the daily driver.
Yep.
It's a little too much for me, being 9 miles out of town, up this hill.
Yeah, I can see that.
All right, what do we want to talk about?
Um, Can you talk about the Lewis structure?
Sure. It's actually super easy. So let's do that. So the Lewis structure is named after a guy named Lewis. He's kind of a sad person, but regardless. What he wanted to do was give an easy way for students to understand what part of the atom, the electrons, how many electrons are going to be chemically reactive in any given experiment. So the Lewis structure for everything in column number 1 on the table is 1 dot. So what he's trying to let you know is only 1 electron is going to be reacting with that. And that's really easy with hydrogen because hydrogen only has 1 electron. But right underneath hydrogen, we've got lithium, which also has 1 dot. Even though it has 3 electrons, 2 of the electrons are utterly and completely off limits and will never chemically react. But the 1 electron on the outside is ridiculously reactive. All of your phones are working with that 1 electron. And then underneath that, we've got sodium, also 1 dot. Potassium, also 1 dot. Rubidium, 1 dot. Cesium, 1 dot. And then francium, there's like none of it on the planet, so it doesn't really matter, but it would also have 1 dot. So do you remember last week, or I think it was last week, we were talking about why the periodic table looks like it does?
Was it set up in groups of like reactivity, I guess, or
So
kind of how?
can you tell me why all of these atoms in the first column react the same?
Because of the amount of neutrons that are on them?
Ugh, wrong word.
Electrons?
Electrons.
Sorry, yeah, electrons.
That they all have 1 electron on the outside that react chemically the same. So they do the same kinds of things. So if you put lithium into water, it will actually catch on fire. So what do you think sodium will do when it goes into water?
Fire.
Bigger fire, but fire.
Bigger fire.
Potassium,
Same thing, but bigger.
bigger fire. Rubidium, bigger fire. Cesium, bigger fire. We don't have enough francium to do it, but if you were to drop like 2 grams of cesium into, say, a bathtub, the bathtub would explode, break into pieces. It'd be like dropping a depth charge into the water. And the rubidium would be like dropping a hand grenade into water.
Jesus.
So they all are very chemically reactive because that 1 electron, that 1 electron really wants to react. But if I move over 1 column, So what's right next to the lithium on the table?
Beryllium.
Beryllium. It gets 2 dots. And what's underneath the beryllium?
Magnesium.
Magnesium gets 2 dots. And underneath that,
Calcium.
calcium gets 2 dots. These all chemically react very similar to each other. Why? Because everybody in this column has 2 dots. So column 1 is 1 dot. Column 2 is 2 dots. We're going to skip over the entire middle section. These transition metals, they don't play by quite the same rules, so we're going to skip those, and then we're going to get ourselves over to
13.
boron. So how many dots do you think boron has? 3. I know we jumped a whole bunch, but look at the number above the lithium, the number above the beryllium, and the number above the boron. 1, 2, or sorry, 3, 4, and 5, right? And what does that number mean? The 3, 4, and the 5.
How many neutrons are in it? Or no? Is it neutrons?
Nope, the other one.
Electron.
Mm,
Proton.
protons. So that number, this number here that's saying that this is element number 1 is saying it's got 1 proton in it. So if you're an atom, you have your proton number and your electron number are equal to each other, always. So if I'm talking about a lithium atom, tell me how many protons are in a lithium atom.
3.
3. How many electrons are in a lithium atom?
3.
1.
3.
Oh.
How many of those 3 react?
1.
1. So it gets confusing because you see 3 electrons with the lithium because it's got 3 protons, so it has 3 electrons. But what Lewis is trying to tell you is only one of them react, and that's why they're in column number 1. So then I move over to beryllium, and beryllium has 4 protons. I know that because it's element number 4, so it has 4 electrons. But Lewis is trying to tell you how many of those electrons react, and the answer is 2. And how do you know that? Because it's in column number 2. Okay? So beryllium is element number 4, boron is element number 5. So I'm skipping all the way over. So how many protons does boron have?
5.
Correct, because it's element number 5. So how many electrons does it have?
5.
5. And so of those 5 electrons, how many of them chemically react?
3.
3. How are you supposed to know that? Because it's always one more than the last one. So then this next one over is carbon, and then nitrogen, and then oxygen, and then fluorine, and then neon. So I'll change colors here so it's a little easier to see. Go to green or something. So how many dots does carbon get?
6.
No, it has 6 protons, so it has 6 electrons, but not all of them react. So how many did beryllium have, or boron have?
2.
There's only 3 dots around this. So how many does carbon get?
4.
4. And how many does nitrogen get? 5. And oxygen?
2.
And then fluorine?
7.
And then neon?
8.
And neon doesn't react. So no elements that have those 8 around the exterior chemically react. So everything below neon, none of those things react. And the helium above it also doesn't react because with helium it only needs 2. So we haven't gotten to this part yet, but you asked me about Lewis structures, and all Lewis structures are telling you is the number of electrons that chemically react. So when a carbon goes in and has a chemical reaction, how many of its 6 electrons are going to be involved in a chemical reaction? 4. So how are you supposed to know that? So, sorry. This column has 1 electron that will react. This one has 2. This one has 3. This one has 4. This one has 5. This one has 6. This one has 7. And this one has 8, which means it won't react at all. So the goal of all of these atoms is to look like the atom in the column on the far right.
Get a total of 8.
Or, yes, but basically, for the most part, yes. It could be 2 as well. So if most of the atoms are just looking for 8. So let's work with the 8 for a second. So if you're a fluorine, how many electrons are you trying to get?
7.
You have 7 that are chemically reactive. How many are you trying to get?
1.
1. It's missing 1 electron right here. If it gets that 1 electron, then it's going to look like neon. So what do you think fluorine atoms do when they're out in the world chemically reacting?
I don't know.
They're out stealing 1 electron from somebody. That's what they do.
What do you call the elements in that column?
Halogens.
They're what?
Halogens.
Halogens.
Yeah. You've probably heard that word before with lights.
Yeah.
Yeah.
Is that related at all?
Oh, yeah. Yeah. We can talk about that after I get finished with this. So fluorine is very, very chemically reactive because it's just trying to do one thing. All right. So my analogy with this, I have a couple. One is, let's say that you were building a fence and you had 1 more plank to put up and your whole fence was done. Okay. Is it going to be very hard for you to finish that? Are you going to be excited to get that last plank put on?
Yes.
Are you going to like, all right, it's noon. I have 1 plank left. It's 12 noon and I take lunch at 12 noon. Do I leave and go eat for an hour and come back?
No,
No.
I'm gonna hustle through and get that board.
I put that 1 damn board back up there. So what's fluorine trying to do? Get
Trying to
1
get that
electron.
damn board.
Give me that 1 damn electron. And so we talked about fluorine in the halogen column last class or last meeting. What did we say fluorine is really good at? Fluorine and chlorine and bromine and iodine. Not cleaning, disinfecting, killing stuff. So
Killing stuff.
the only thing that needs to happen to kill something, so when we're talking about stuff, what I really mean is to kill a cell.
Mhm.
So when we're thinking about a cell, there's a membrane around it. And if you puncture the membrane in the same way that if you puncture a balloon, it just deflates and it's not a balloon anymore, it's not a cell anymore, it dies. So if fluorine comes in contact with one of these cells, it takes an electron off of one of the atoms there, and then the cell has a hole in it and it just dies. So if you were to breathe fluorine in, it would kill a bunch of cells inside of your lungs, which could potentially kill you. But most people aren't exposed to fluorine in that way. So you could probably get away with taking a small breath of fluorine and not dying because you're composed of many, many cells. But if I'm a virus or a bacteria or a mold spore and a fluorine atom runs into me and it tears a hole in my cell membrane, what just happened to me? I died because there's only 1 cell and so I'm dead. So we use fluorine, chlorine, bromine, and iodine to kill stuff.
But then change them if will they then pick up like a carbon element out of that process?
Nope, they get 1 electron.
Okay.
So they grab 1 electron. So
Okay.
those things go in as elements and they grab an electron and now they look like whatever element is to their right. So fluorine will now look like neon and chlorine will look like krypton and bromine will look like xenon and iodine will look like radon. And it's because they just gained 1 electron. And that's what they're trying to do. And they're very, very, very good at it. So all of those things do their job very well. What did we say happens in that first column on the far left? It makes water catch on fire. There's not a lot of things that can make water catch on fire, right? But sort of like not what we think about when we think about water. So those are very, very chemically reactive. Are we okay with that? So the things on the edges of the table, with the exception of the very last column on the far right, those are very, very chemically reactive. So why did we say the fluorine column was super reactive?
Because it's eager to get that extra one.
It just had one thing to do, right? Tell me about column number 1.
It has
One thing to do.
7 left, or it has
Yep.
one.
It does the exact opposite that the fluorine does. So the fluorine wants to grab 1 electron and go to 8. And these guys, they all dump 1 electron.
They only have one electron.
They actually don't. So let's look at, I'm going to put up a kind of not true version of what the lithium looks like, but it's fine for our purposes. So we know that the lithium has 3 electrons because it's element number 3 and it has 3 protons. Okay, so what lithium is going to do is it's just going to dump that electron. And then what does it look like? How many electrons does it have?
2.
2. What element has 2 electrons?
Lithium? No.
Helium. How do you know that?
The
Is
right
it helium?
Yep. Yeah, helium. How are you supposed to know that? Because it's element number 2. So it has 2 protons, which means it has 2 electrons. And helium doesn't react. Everybody that's in this column here, this very, very last column, they don't react. So what all the elements are trying to do is to get to a point where they can stop reacting. They're trying to retire. So what did we say fluorine needs to do so it can retire?
Pick one more electron.
Grab 1 electron. What's lithium going to do to retire?
become helium?
Yep. Dump 1 electron, and now it looks like helium. What's sodium going to do?
Dump 2.
No. Why would it dump 2?
Dump 1.
Dump 1. What's potassium going to do?
Oh, I see.
It's trying to be like, okay, dump 3.
Dump 1. What's rubidium going to do? There's a pattern here. Dump 1. What's cesium going to do? Dump 1. What would francium do? Dump 1. How are you supposed to know that? It's in column number 1, so its Lewis structure is 1 dot. So it's trying to give 1 electron away, and that's what they're all trying to do.
But
So
the whole row has 1.
that whole roll has 1 electron that's reactive, and what is it trying to do with that 1 electron? Get rid of it. What's column 2 trying to do?
Get rid of 1.
Get rid of 2. How do you know that? Because it's got 2 dots. What's column 3 trying to do?
3.
Dump 3. What was column 7 trying to do? Or 17, the fluorine column?
Yeah.
Pick up 1.
Pick up 1. What do you think the next column over, the oxygen column, is trying to do?
Pick up 2.
Pick up 2. What do you think
the
the...
ones in the middle then?
we're working towards it. What do you think the nitrogen's trying to do?
Say again?
What's nitrogen trying to do?
Pick up 3.
Pick up 3. What's carbon trying to do?
Dump 4.
I don't know. I don't hate your answer, but it's only half right. What's the other option?
Lose.
Dump 4.
It's right in the middle, right?
Yeah.
So it could give away its 4 electrons, or it could take 4 electrons. So what would determine if what it's going to do? What if carbon ran into fluorine? What would the carbon do with its 4 electrons? What's fluorine trying to do?
Trying to gain some.
Trying to gain. So what would the carbon do?
Lose?
It would just give them to him. It doesn't care. But what if the carbon came in contact with, say, a potassium? What's the potassium trying to do?
Trying to dump some.
So what will the carbon do?
Just take it.
Take it.
Why
So-
is the carbon so agreeable?
It's right in the middle. So
Okay.
So it's 8 total. So group
8.
4 is right in the middle. So just I guess depends.
it depends
Which
on what the
direction?
other guy's going to do. So it's really, what is it easier for fluorine to do? Gain 1 electron or lose 7 electrons?
Gain 1.
Gain 1, right? What's it easier for sodium to do? Lose 1 electron or gain 7 electrons?
Lose 1.
It's always easier to do. It's all of this stuff is like kind of atoms are trying to be lazy. So what can I do what is the quickest way for me to do this? So oxygen needs 2 electrons or lose 6. Well, it's a heck of a lot easier to gain 2 electrons than to give away your 6 electrons. Okay?
Why would the carbon not take 4 from the fluorine?
Because what's the fluorine trying to do?
Become neon?
Okay, so what is it trying to do then?
Even an electron.
It's trying to gain 1 electron.
Mm-hmm.
Okay? And it's the closer you are to the edges, the better you are at doing what you're doing.
Is that okay?
So let me put up another color here. So
So they're more powerful because they're closer to their goal?
yes,
Whether
Absolutely.
they've overeaten or undereaten a little, they're kind of,
so do you collect anything?
do I?
Yeah.
Oh,
Or do you know anybody that like collects stuff? I don't know.
yes.
Okay. What if that person needed to get one more thing to complete their set?
Uh-huh.
Would they be adamant about getting that done?
Okay.
What if there were 50 things in the set and they had 20 of them?
Mm-hmm.
Are they going to be super gung-ho about going out and get 30 of them? Or what if they were at number 49 and they were
Mhm.
one away from finishing up? They'd be more.
Is there like an actual energetic element to that? Or, oh, wait a minute.
The elements themselves are attempting to become stable in a way where they'll
Mhm.
stop chemically reacting. So in nature, everything that is happening is trying to give away its energy. So fluorine becomes less energy if it gains that 1 electron. So, I mean, an easy example is you have a hot cup of coffee, it's sitting there, you don't touch it, you come back in an hour, it's cold. So that's what nature is trying to do. It's trying to get rid of energy. So a fluorine that is very, very chemically reactive can just get that 1 electron, then it's finished. And it doesn't do anything anymore. So what nature wants is everybody to be satisfied and stop doing stuff. All right. So what is it easier to do? For fluorine to get that 1 electron and become satisfied, or for carbon to try to grab 4 electrons and become satisfied?
Mm-hmm.
So it's harder for carbon to do it. So carbon's sort of like that wishy-washy friend, or like, what do you want to eat for dinner? What movie do you want to see? Whatever you want. I don't care.
Or your spouse.
Or your spouse, whatever. Are you telling your significant other they're carbon? I hope not.
Yeah.
Okay, so if I'm on the outsides of the periodic table, with the exception of the final column, the outsides of the table mean I'm really reactive. And how do I know that based off of what we talked about? The fluorine column kills anything it comes in contact with. So that's obviously really reactive. Are you worried about grabbing a charcoal briquette?
If it's heated, yes.
No,
But
no, just a charcoal briquette. Just like grab one
No.
out of the bag. No,
No.
it doesn't matter. Why? That's pure carbon. Why are you not worried about it? Because carbon's wishy-washy. It doesn't really care about gaining or losing its electrons. It's got like, it's hard for me to gain or lose 4, so I'm just going to sit here and do nothing. All right? So that same person who was building that fence, if they were halfway done with the fence and it was noon and it was lunchtime, are they going to keep working and finish the fence? No, they're going to go to lunch. That's what carbon is. Carbon's the I'm going to go to lunch guy. The rest of the elements are a little more intent on doing something. All right, think about it another way. If you had one kitten and you were sitting out in front of Rose Hours and you were trying to give it away, it wouldn't take you that long. But what if you were sitting there with 4 kittens and you had to give them, you were like, no, all 4, they're brothers and sisters and they're all going to the same home. How long is that going to take you to give those 4 kittens away to one family? Hard. So carbon, if you have a bag of charcoal in your garage, you can leave it there for hundreds of years and it won't do anything. Well, it's like you would be sitting there for hundreds of years trying to give away those 4 kittens. So if you have more to do as an atom, you tend not to do it. If you have less to do, you tend to be very, very adamant about getting that one thing done. So fluorine's column is all trying to get 1 electron. And we know that because Lewis said in that column you put 7 dots around it, which means it's 1 away from the last column, so it's got 1 thing to do. And on the other side of the table, the hydrogen lithium column, they have 1 electron. So all they need to do is give away that 1 electron. So they're really, really good at giving that 1 electron away. And as they get closer to the middle, and the carbon is the middle, it becomes less and less good at doing that thing, whatever it's trying to do.
Is that why they give charcoal pills to people who've like ingested poison?
Yeah. The charcoal itself is it can be like fiber and push it away, but also because usually the things that kill people and are poisons are metals. And so what metals are trying to do is give their electrons away, and carbon goes in and gives its electrons away. And when it gives its electron away, it detoxifies that thing, and the carbon itself doesn't kill you either. So it's really important that if you're going to give somebody something to take care of one problem, that it itself doesn't cause another problem, right? So the carbon is so like, nah, it can help out with a problem without causing another problem.
Right.
Okay, so again, forget about that middle part, that transition metals where it goes from scandium to zinc. The elements, we'll call them columns 1, 2, up to 8. Those guys have that number of dots around them, and that's telling you how many electrons it's trying to get rid of or needs, and how chemically reactive it's going to be. So does that answer your Lewis structure question?
So the number under, like, like carbon 12.01, is that the number of protons it has?
The number above it is.
The number above it is.
The number below it is the number of protons and neutrons it has. But we talked about this last time, it's an average, a weighted average. So if the carbon's mass is 12 and you know it has 6 protons because all carbons have to have 6 protons, then it also has 6 neutrons because they have the same mass. I feel like I pushed a question off that you had, Sarah. Do you remember what that question was?
Is that to me?
Yeah, while we were in the middle of that Lewis structure discussion, you asked me another question, and I said I'd tell you in a minute after we finish with this.
I forgot.
She was wondering why we were skipping the transition metals.
Is that what it was?
I think that's what you were saying, Sarah. You're wondering why we're skipping that.
Yeah, I don't think that's what it was. I feel like it was something else.
I have a new question now.
Okay, go ahead.
So I'm looking over at argon, something about the mass. You're talking about the weighted mass being balanced between the protons and neutrons with carbon, where you've got the six indicating the six electrons and
Protons.
the six protons.
Yeah.
Okay. And okay, six protons and six electrons.
Yes.
Okay.
It has to be that way because the electron number can change and the proton number can't change. So if I'm a fluorine atom and the number above me is 9, that means I have 9 protons. That doesn't necessarily mean I have 9 electrons. I could have 10. If I'm an atom, I definitely have 9 protons and 9 electrons. But fluorine is really reactive, and so if it gets released or allowed to react, it immediately gets a 10th electron.
Oh, okay. I thought that it was the same number of protons and electrons.
It is if it's an atom.
Okay.
So I'm stipulating that because as soon as they react, they're allowed to chemically react, the electron number is going to change.
Okay.
But the proton number will never change. So that 9 above the fluorine literally means 9 protons. And then you can say, if I'm talking about an atom, then I know it has 9 electrons because I know it hasn't reacted yet.
Protons and protons will never change.
Never change. Chemistry cannot change the number of protons or neutrons inside of a nucleus. Not possible. I mean, we can do it, but it's not a chemistry thing. It's a nuclear physics thing. Sorry, Sarah, you were asking me a question about the number underneath the argon?
Yeah, so that's it implies that it's not balanced.
So we're talking about argon. Ooh, I don't like that.
I'm just noticing that 18 and 18 is not 40. Am I making things up?
No. What's the number above the argon?
18.
So what's that 18 mean?
That's the number of protons.
18 protons. Okay.
Yeah.
And this number at the bottom is, what is it, 39?
0.948.
Okay, great. So I'm kind of sad because we talked about this last class. What does this number underneath here mean?
The weighted.
The weighted mass.
Yeah.
Yeah.
It's the number of protons and neutrons in the nucleus. Okay?
Oh, yeah.
So it's the mass. Okay, fine. So protons and neutrons and electrons, and then the unit we use for the mass is an AMU, and the proton number is 1, and the electron number is 1, and the neutron number is 1, and the electron number is 0. So if I'm an atom and I lose or gain an electron, my mass doesn't change because it has a mass, but it's so small that it doesn't matter. My example was if you lost a hair, it's not like somebody's going to say to you, hey, did you lose weight? Like, nobody's going to notice. It's just like nobody's going to notice that an atom lost an electron because it's such a small amount of weight. So this argon value here, it should be a whole number. But it's not a whole number because this is the weighted average. So do you remember us talking about the weighted average? So if this is going to be a whole number, what whole number would it be? This.
40.
40. Okay, so if my argon has a mass of 40, and most argons do have a mass of 40, what I know the 40 is due to 18 protons plus 22 neutrons. How do I know that? Because the mass number is the number of protons plus the number of neutrons, and I know all argon atoms have 18 protons. They have to, period. That's the definition of an argon atom. So all the rest of the mass has to be neutrons. So why is this number not 30? Why is this number not straight up 40? because there are other argon atoms out there. Some argon atoms have a mass of 39. So what's inside of the argon atom that has a mass of 39? Oops.
Radioactive.
No. What do I have written here?
Eighteen protons plus 21 neutrons.
So what's the difference between this one, which is called argon 39, and argon 40? One has one more neutron in it.
Yeah.
That's it. These are isotopes. And the definition for your isotope is it's an atom that has a different number of neutrons. So this doesn't change the chemistry of the atom, because the chemistry of the atom is dictated by the number of electrons. And so how many electrons do argons have? They have 18. How do I know that? Because the argon atom has 18 protons in it. And the argon atom is going to have 18 electrons in it. How do I know that? Because it's in that last column, and all of those atoms. What's the Lewis structure look like for argon? How many dots?
8.
And that means it doesn't react. So I know it's got 18 electrons, because argon's always going to have 18 electrons because it doesn't chemically react. So where is this 39.948 number coming from? Remember we were talking about you got an A and a B. Oh, sorry, that's not what we did. We said an A and
And the
an
average
A and a
of
C
them,
and a
like,
C. And so this average is a 3.0, right? Like if you got two A's and two C's, your GPA is a 3.0. But what if you got an A and an A and an A and a C? Is it still 3.0?
No.
No. Why? Because you got 3 A's. So your weighting is more towards the 4.0. So this is, I don't know what it is. It's going to bug me until I actually do it.
3.5.
14 divided by 16. Oh, yeah, you're right. It's 3.5. So this is a 3.5. Well, why is it a 3.5? Because the average of an A, which is a 4, and a C, which is a 2, is a 3. Well, it's not a 3 because you got 3 A's. So tell me why this number is 39.948.
Because it's an average.
It's a weighted average, not an average. So, because if this was just a straight up average, the number would be 39.5. But it's not 39.5 because when I go looking for argon atoms, it looks like if I had 1,000 argon atoms, 948 of those will be argon 40, and 52 will be argon 39. So since most of the argons in the universe have a mass of 40, the average atomic mass, the weighted average atomic mass, is 39.948. So when we look at that carbon number and it says 12.01, what that's telling you is if you were just grab a carbon atom and check its mass, almost every time you did, the mass would be 12. But sometimes it's going to be bigger than 12. And how do I know that? Because the number is not exactly 12. It's a little bit bigger than 12. So some have a mass of 13 and some even have a mass of 14. Does that make sense? Okay. So can you tell me about chlorine?
It
How
has a
many-
mass of 12.01.
Chlorine.
Chlorine?
Chlorine.
I don't know.
3.
It's number 17.
It has a mass of 35.45, and it has 17 protons and 17 electrons.
Right? That's good. So this chlorine's mass is about 35.5, right?
Mhm.
And I know all of them have 17 protons. So most of them have 18 neutrons or 19 neutrons. Are we okay with that? And how do I know that? Because this thing here has a mass of 35, and this thing here has a mass of 36, and this is about right in the middle. So if you were to grab a chlorine atom and check its mass, it's about 50-50 that it'd be 35 or 36. Does that make sense?
Mhm.
Okay.
So it either has grabbed that extra one or it hasn't.
Yeah.
In a
Way, manner of speaking, but with neutrons, those are in the nucleus, so those are off limits. So when you say grab, it's like grab's a bad word. The way this got,
born with an extra toe.
I like that, formed. Yeah, they don't go off and react to form nuclei. They were created, and then they're stuck with what they got. So when that chlorine was created in the middle of a star that's undergoing fusion where it's slamming atoms together, and when that star blew apart and that chlorine ended up here, when it was made, it had 18 neutrons in it, or it had 19 neutrons in it, because about half the time each of those two different chlorines were created. Okay,
This lesson was very helpful,
that's good.
putting it into I guess just a different perspective.
I always think it's helpful when you hear it a second time, especially when you
Yeah,
never heard it before and you're like, what? And you're like, oh yeah, that sounds.
Not everybody learns the same way, so
So if the mass is 35.45, do we round that up when we
Nope.
figure out the protons and neutrons? Or
Nope.
the neutrons?
You can't figure it out.
Oh.
You can guess as to what it might be, but you cannot figure out what the actual neutron number is going to be. You can tell me the protons and the electrons because it's going to be 17 for both. But if I was to say, tell me the number of protons and neutrons and electrons in this atom, I would have to give you something like S33. I would have to give you that, where there's no ambiguity in it whatsoever. There's no decimal places. There isn't any ambiguity. So tell me, how many protons does this isotope have?
is it sodium?
No. Sodium is Na.
Oh,
How many protons?
Yep.
16.
16. This is sulfur, and sulfur's element number is 16, so it has 16 protons. So since it's an atom, it has 16 electrons. How many neutrons does this sulfur have, this isotope?
We don't know.
You do.
17.
So 33 take away 16.
Yep. 33 take away 16 gives us 17. That's how you
Just
know.
the difference, basically.
It's just, well, what I know is this number right here is the addition of these two numbers. And I'm 100% sure that there's 16 protons because we're saying this is sulfur. So all the rest of the 33 has to be neutrons. All right.
Mm.
So tell me, I don't know, tell me about,
There's always more neutrons than
No.
protons.
no,
No,
could be the same.
oh, but not less.
It could be. There's one proton in that hydrogen and there's no neutrons. But for the most part, it's either the same or there's more neutrons. Do you remember why we said neutrons existed?
To
The balance?
separate them.
Yeah, so if I'm a helium atom, I have 2 protons in my nucleus. So I'm a positively charged something or other. And I have to sit right next to another positively charged thing. And I don't want to do that. So instead of them being directly on top of each other, nature shoved 2 neutrons that don't have a charge in between them. So remember we were talking about a 4-year-old and a 4-year-old that were fighting, and you put a wall between them so they can't attack each other? That's what's going on here. So the neutrons are just buffering the positive charges that have to be really close to each other, but the neutrons keep them from actually sitting on top of each other. Okay, so tell me what's in this sodium, this Na.
11 protons and 12 neutrons.
And electrons?
11.
So I know that there's 11 protons because it's sodium, and the rest of this 23 would be 12 because that's the only number we have left to deal with is the neutron number. Okay. I think you guys got that.
I think, okay, I get that now.
Who's here? How many people are actually here? Stop sharing. Did all of you guys do the quiz?
I haven't yet.
No? Okay. We'll talk about it on we'll talk about it on Monday then.
Does it due Friday or Saturday?
It's due on the 17th, so it's due on Friday.
Okay.
Okay.
And the quiz is on chapter 1.
No, it's not.
Chapter 1 and 2?
No.
Oh, it's on the, oh yeah.
It's on the
okay.
website.
Yeah.
Okay. Let's see. Anybody want to talk a little bit about naming stuff for a little while, or do we want to move on to stuff for chapter 2?
We can do chapter 2. I'm almost done with chapter 2, so.
All right, so we've kind of just covered a little bit of chapter 2, actually,
Yeah.
because we were doing Lewis structures and talking about the elements. Okay. So the other thing with Lewis structures, let's do a little bit more with Lewis structures. So how many dots does a carbon get based off of its position?
4.
4. So how many dots does an oxygen get?
6.
And these atoms, they're trying to get how many dots around them.
Million?
8.
They're trying to get 8. Remember, they're trying to look like the column on the end. So for carbon and oxygen, they're trying to look like neon, which has 8 dots around them, right? All right. So if I were going to put carbons and oxygens together, and I'm going to make carbon dioxide, let's look at what the Lewis structure of that's going to look like, okay? So here's a carbon. Oops. A dot, and a dot, and a dot, and a dot. And then here's an oxygen. Dot, 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 dot. Oxygen. Dot, 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 dot. Oop. Messed that up. Sorry. Just a second. Thing's fat. Okay, so are we okay with seeing the oxygens both have 6 electrons around them and the carbon has 4 electrons around it?
Mm-hmm.
Okay, so
It can steal one from each side, and then that becomes a molecule.
it doesn't steal it. When they're in the molecule state,
It smushes.
I just circled that oxygen on the left. How many electrons does that oxygen look like it can see or have access to?
8.
8. So it's happy.
So they're like sharing it.
They are sharing it. So how many electrons is the carbon seeing?
8.
8. And how many is this oxygen seeing?
Same.
8. So they're all happy. What do you know about this molecule?
Yeah.
Right? It's inert. What do we use carbon dioxide to do? Put out fires. You take a carbon dioxide extinguisher and you put it on top of a fire and the fire goes out, right?
Mhm.
If you have a candle that's burning, like a Yankee candle or something like that, and you put the top on it, the inside uses up all the oxygen and it's just filled with carbon dioxide now, the candle goes out. Why? Because carbon dioxide's inert. Why? Everybody's happy. And what I mean by happy is you see 8, you see 8, and you see 8. So nobody's going to chemically react. We okay with that? So let's do so that was a covalent bond. And a covalent bond happens between nonmetals, and the nonmetals were the ones that are blue on the periodic table, everything on the far right of the periodic table. So if you look at those names, you know that they're not metals, right? Oxygen isn't a metal, it's in the air. Nitrogen is in the air, it's not a metal. Carbon, I mean, that's a charcoal briquette, you know that's not a metal. And you look at stuff on the left side of the table, you've got iron and gold and silver and platinum and zinc. Those are metals. So the green stuff, those guys are metals, and the blue ones, those guys are non-metals. So if I chemically react two blue things together, I get a covalent bond and everybody shares. If I chemically react something from the blue area with something from the green area, that's called an ionic bond. And there isn't any sharing. The metals give their electrons to the non-metals. And we should kind of know that based off of what we talked about a little bit earlier. What type of atom is fluorine? A metal or a non-metal?
Non-metal.
It's a non-metal. So what do you remember fluorine wanting to do with electrons?
Take one.
Take. Okay, so fluorine is a non-metal, and non-metals want to take electrons. So sodium, what kind of substance? What kind of atom is that? A metal or a non-metal?
Non-metal.
Sodium's a non-metal. Why are you saying that? S is sulfur.
Sulfur.
I'm talking about sodium.
Oh.
Sodium a metal?
Sodium's a metal.
So weird.
Yeah, because you'll never see it in its metal form because it's so chemically reactive. The moment it's exposed to air, it rusts. Like you could watch it. It's super soft. Like, you know how lead is really soft? Sodium is like butter that's come out of the refrigerator soft.
What makes it a metal then?
It is a metal. Like if you look at it in its elemental state, if I showed you it in its elemental state or you watched a YouTube video on it, you were like, oh, that thing's a metal. It's what metals are, or they're shiny, they have luster, they can be pulled into wires or ductile, but really what makes a metal is they give away their electrons. They conduct electricity, they conduct heat, they give away their electrons. So what's everybody in column number 1 trying to do?
Give away their electrons.
Give away 1 electron. So that makes them really, really metally. So if you watched a YouTube video on sodium, somebody would like take it out of like not petroleum jelly, but like mineral oil. That way it's not being exposed to the air or water. And then they could just cut it with a butter knife. That's how soft it is. But you'd look at it and be like, yeah, that looks like a metal, just a really soft one. I mean, are you okay with me saying mercury's a metal?
Yeah.
Yeah.
It's a
Because
liquid.
it's shiny.
It's shiny, right? It conducts electricity. It conducts heat. It gives its electrons away. So just because it's a liquid doesn't mean it's not a metal. And just because sodium is soft like butter doesn't mean it's not a metal. I don't have to
How
be...
conductive is sodium?
What?
How
Conductive?
Yeah. Is
It's...
that the right word? I don't know.
Sure. It's conductive. It's just kind of useless because the second it touches air, it reacts. So I'm sure you've seen copper wire before, and it stays copper wire forever. Sodium doesn't do that. It reacts chemically immediately as soon as it's exposed to air. So if you were to take that, like a little, what I've seen is something about the size of your finger, and somebody cuts it, and the inside of it is super shiny. And as you're watching it, within 1 second, it becomes gray. Why? Because the air turned it into sodium oxide. It rusted that fast. So it wouldn't make wires out of sodium because they would rust immediately. upon making.
Huh.
So what would you want to make wires out of? What would be a really good quality to have in your wire?
Copper.
No, what's a good quality?
Oh, solid.
Oh, okay, maybe.
Um,
How about it doesn't rust?
Yeah, okay.
What I don't want my wire to do is rust. So even though sodium's a really good conductor, it rusts in seconds. So I wouldn't want to use that. Does that make sense?
Mhm.
All right, so back to our discussion. Sodium wants to give an electron away. That makes it a metal. So sodium is giving electrons away to something that wants to take electrons, the fluorine. And so here's my sodium, and here's my fluorine. And remember, fluorine gets 7 dots because it's in that second to last column. So what's going to happen with this one electron? What's the sodium wanting to do?
Give it to the fluorine.
And now that fluorine has that electron. This is
It
the,
doesn't just give it, they share it, right?
nope,
No. Oh,
it
okay.
does not share it. The sodium doesn't want to share it, and the fluorine doesn't want to share it. So they don't. So I can't really say fluorine is stealing it, because can you steal from somebody if they're trying to give you something? No.
So then the sodium just ceases to exist?
No, it just loses the one electron.
Oh, okay.
That's it. It gives its one electron away, and then it looks like neon. Its electron configuration looks like neon. Because how many
Right.
how many
Okay. So
protons?
then they both become neon.
It doesn't become
Got it.
neon. No, it just has the same number of electrons that neon has.
Oh,
So is neon chemically reactive?
no.
No. So is sodium that lost its one electron chemically reactive?
Oh,
And that's what nature's trying to do with all the atoms.
Hmm.
So is fluorine chemically reactive? Yeah, it will kill you.
that's
What about a fluorine that's gained one electron?
No.
No. After they've done their thing, they're spent. So do you think it would be smart to take a wire and put one end on one side of your car battery and put the other end on the other side of your car battery?
if you want to blow it up.
You wouldn't blow it up, but you'd melt the wire. So, but what would happen if that battery was dead? What if I put the wires on it then?
Nothing.
Nothing happens. So what nature's trying to do is make everything dead as far as their ability to react. So all day, your cell phone is taking the one electron that the lithium has and gives it away to run your display or text or make a call. I mean, nobody does that, but to display or text, right? That's what that one electron is doing all day. And the lithium wants to give it away. And how do we know that? It's in column number 1. And it's really good at giving one electron away. So all day, the electron, all the lithiums in your battery are like, take. And your phone is using it to work. And then at night, what do you make the lithium do?
Charge it back up. Give it back up.
Take that damn electron you never wanted back, and then give it back to me tomorrow. That's what's going on. So
What's that process of drawing that electron?
the lithium wants to give the electron away really bad. So all you need is something on the other side of the battery. So the way the battery is going to work is, in a cell phone, they usually look like this, just like little squares that are, I don't know, maybe 3 or 4 millimeters thick. And this is the negative side, and this is the positive side. So this is where the electrons come from. So the lithiums are over here, and they're giving the electrons away. And then this is your phone. It's running the display and doing all the rest of the stuff. And then the electron comes here to something like, I don't know, it doesn't really matter, carbon. So remember what we said carbon does?
Nothing.
Gives it away.
Or takes them,
It's
right?
neutral-ish.
It's neutralish. It'll give electrons or it'll take electrons. So this carbon's got 4 dots. And this lithium's giving an electron away. So if the carbon gains an extra dot, fine. That's fine. So all the lithium needs is a place for the carbon to for its electron to go to. So it's going to sit on top of this carbon, and then at night you use electricity to take that electron and force it back over to get put back on the lithium.
Wow.
So it's kind of like, let's say that you were at the dinner table with a bunch of people and you were going to get up and go get some water. And on your way back, someone's like, hey, can you grab the salt shaker? I mean, you were walking that way anyway, right? You were going over, you were going to make that motion anyway, go over there and then come back. So is it any big deal for you to grab the salt shaker on the way back? No, it's not. So the way your phone is using, the electron leaves the lithium because the lithium doesn't want it. And on its way to the carbon, you make that electron do something. And what it's doing is showing you, making your phone work, or making your headphones work, or making, I don't have any other battery powered stuff. Oh yeah, or making this pen work, right? So you just make the electron do something on the way to doing what it wants to do anyway, which is to go to an atom that wants the electron more than the lithium does. Is that all right?
Okay, that makes sense.
Our issue with batteries is, how long does it take for me to get that electron to go back onto the lithium? If we could make that happen really fast, everybody'd be a lot happier with electric powered vehicles, right? Because right now it's fine if you have a Nissan Leaf or a Tesla and you're driving around town, or maybe even driving to Portland. But if you've got a pickup truck and you need to go get like a load of rock while hauling a trailer, and the thing dies in 100 miles, you got to drive to, I don't know, Pendleton and go pick up a horse and come back, and it takes
SOL.
6 hours to recharge your battery. You're not going to do that. That's not going to happen.
Mhm.
So if we could make that charge process take the same amount of time that it takes to fill up a car with gasoline, then we're going to be down with that. So we're getting there. We'll get there at some point.
What do you think about that new Tesla truck?
It's ugly.
Oh, ugly. God.
I don't think it's ugly. I just think it's interesting. It's not like a good truck. Like, it's guys who have trucks aren't going to buy that.
Yeah,
That's a truck to drive around. That's like a Hum 3. Like, who drives a Hum 3? Not somebody
mall
who's
hopper.
not, yeah, a mall hopper. Not somebody who's working. Somebody who's dragging a bunch of kids to a soccer game in Portland. Like, that's what that's for. It's not for
Yeah.
working. If you had a Hum 1, that's a different story.
Definitely.
So Ford has an electric truck prototype that's supposed to come out, be full production in December. The truck looks like you couldn't tell the difference. It's an F-150 body style. It doesn't look anything different than the regular truck. And so the guys who are gonna buy that truck are gonna buy it, one, because it doesn't look like the Tesla truck, and two, it needs to have a really, really long tow capacity or drive capacity. Their big deal is going to be, you can bring your shop table saw with you and plug right into the side of the truck. And the truck is your workspace. So you can plug it into a 110 outlet and run your table saw and run all you don't need any battery powered stuff. You're literally just going to plug into your truck and work all day and then go back to your house and charge up. So it's just, is Ford going to be able to make that battery last long enough for your average user or not? I guess
Probably not. Depends on how much you're going to be using on your construction site or whatever projects you're going to be doing.
it's totally not about what happens at the construction site. It's going to be about how far is that construction site away. If you're driving your truck around Portland, or if you're driving your truck around Hood River or the Dalles or something like that, it doesn't matter how long you're at the job site. That battery ain't going to go dead. But if you have to get up at 4 o'clock in the morning and drive to Pendleton to do a job, you might not be able to get back without charging along the way. So it's really about the travel time, not
to get to construction sites.
yeah. I mean, running a table saw off your truck battery is going to be nothing. Driving the
Yeah.
truck is going to be a big deal.
Yeah. So for a local company, it would be probably worthwhile but for one that has to travel or something, probably not.
So if you're like a big general contractor, maybe 20% of your workforce are the electric trucks to make it easy on you for local stuff, and the rest of the stuff has to be diesel powered or gas powered
Yeah.
until they make the battery last longer. So if you can figure out a better one of these batteries, I mean, you become a gazillionaire immediately. That's pretty much what we're looking for. The best possible battery.
Why don't they make it out of like francium rather than lithium?
There's less than a teaspoon of francium on the planet
Oh,
because it's too it's radioactive. So the moment it's formed, it unforms itself. But lithium is a better battery source than anything else in that first column anyway. One, because it's the lightest of those elements.
Hmm.
So the density of water is 1. Anything less than 1 would float on water. Iron's density is like almost 8. Copper's density, which batteries can be made out of, is almost 9. And lithium's density is 0.5.
wow.
So it's very, very light by comparison. So a lithium ion battery doesn't weigh very much for how much energy it has by comparison to, say, a nickel cadmium battery, which is the old rechargeable batteries that we used to use. Or, I mean, what's the battery inside of your car made of?
No idea.
Lead.
Really?
Have you picked one of those batteries up?
Yeah.
They're heavy, right? It's lead. What's lead's density? Well, it's a heck of a lot more than 0.5.
Yes.
I think it's 11 and a half, somewhere around there. So lithium is 22 times lighter for the same size than lead is. So if you built that car battery out of lithium, it would weigh 22 times lighter. It has other issues, which is why those batteries aren't made out of lithium, but we probably don't have time to talk about that right now.
Doesn't it lose its conductivity? Let me know if I'm making up words.
No, they both, all batteries will lose their ability to be charged and recharged over a period of time. Lithium does a really good job. Takes a long time. The old rechargeable batteries that we had were good from like 20 to 40 recharges. And those were the nickel cadmium batteries. Lead acid batteries are really good. They'll last for, I mean, when was the last time you changed the battery in your car?
Yeah.
So the downside of those batteries is they're made out of lead. So they weigh 50 to 75 pounds, if not more. So
Does the lithium inside the battery then become something else if it's no longer being conductive?
it goes from being an atom to being a molecule. And so it'll probably turn into something like Li2O, which is just rusted lithium.
Oh.
And rusted lithium doesn't have an electron to give away because it already gave them to oxygen. So it can't do its job. So at some point, the lithium is going to be giving its electrons away and giving its electrons away, and then eventually it's going to turn into this. And then that's when the battery isn't going to work anymore. So then I have to disassemble the whole battery, break this apart using a great deal of voltage and get my lithium back and then make a new battery with it. So you should always read.
But you can break it apart?
Oh yeah.
The
You can't do it at like your house or anything like that. It's
Right.
something like a manufacturer would do. So don't ever throw your lithium ion batteries away for many, many reasons. One, they're super valuable. Like people will buy them from you. And anybody who takes batteries would love to have your lithium ion batteries. Like the hobby shop in Hood River, they'll accept all batteries because what they really hope is you give them lithium ion batteries because then they get a credit on buying the lithium ion batteries for all the RC cars that they sell. I think if they give back like 10 dead lithium ion batteries, they get a lithium ion battery. And those batteries are anywhere from $20 to $100.
Wow.
So can you use that same process with lead?
Yep.
Like a lead battery and like electro
Yeah,
separated?
so that's why
And
when you
what's the byproduct of that though?
it's lead that they
Okay.
want. So that's not it's not like it's going to get released to the environment because they need the lead to put in the new battery. So like if you go to buy a new car battery, you can either bring your dead car battery and turn it in, but if you don't turn in a dead car battery, they'll charge you like $15 to $25 depending on the battery, and it's called a core fee because they want the old battery back. So you might go to Walmart and it'll be like $75 for this battery. But if you bring your dead one back after you install that one, or you go out into the parking lot and swap them out, which probably happens more often than people want to admit, and walk back into Walmart, they'll give you that $25 back because that dead battery is still valuable to the company. They'll take it back and then they'll separate them into the components and then remake a new battery out of it. At first, lithium was super hard for us to find. So we were very interested in scavenging all of those dead batteries. Now we have a little bit bigger source because Bolivia found a bunch of it.
So if these elements can be separated via electricity,
Yep.
all of this, all of these, you know, mixtures and
Molecules.
anyway. Okay,
All of these
that-
molecules that get made.
Right. So like take Australia right now. There's all of this smoke and nastiness going up into the air and it's actually creating lightning storms.
Yep.
So does that occur naturally then? That kind of electricity in the air, does that have the does that then
It's
kind of
literally
blast
it's
those guys
static
apart?
electricity. It's just static electricity. It has absolutely nothing to do with things chemically reacting. In the exact same way that you can generate static electricity with your hair in a balloon, that's exactly the same process that's happening when dust particles leave the earth and go into the air. So you end up with clouds that have the one side that's either positively or negatively charged, and the ground's the opposite charge, and then they need to discharge each other. So it's basically like a tiny battery is formed. Well, not a tiny battery, a really big battery that can't sustain itself, and so then the electrons have to go back to where they were before.
Okay, but then is that electrical current that's running through the atmosphere, is that blasting apart like these little
Yeah,
molecules?
and bad
that
things are
around?
happening. So like you've got an oxygen. So this is part, the book talks about this. So you've got oxygen atoms out there, a bunch of them in the atmosphere. And when the lightning goes through, if it strikes this one, it'll break it up into two oxygens. And oxygens hate to be by themselves, hate it.
Okay.
So hydrogen, lithium, oxygen, fluorine, chlorine, bromine, and iodine. These are called the diatomics, and in nature, they're always found paired up, always. So that's why you're breathing in O2 and not just O. So if this guy here, this oxygen here gets broken apart and this O is available, this thing is doing anything it can. If it can't find its partner, if it's too far away, it'll see this oxygen and be like, hey man, I just need a break. I can't be by myself. And it'll turn into this. So what's wrong with
Okay.
that?
Right.
What's this?
Yeah. Okay. And you can smell that sometimes when there's a storm brewing.
No.
No?
The answer to that is no, but your reasoning is correct. Ozone
Okay.
itself doesn't have a smell, but ozone is so darn chemically reactive. When this thing runs into the nitrogen in the air, which this is about 80% of the atmosphere, and oxygen is
Right.
about 20%. So when these guys run into each other, you're going to end up making molecules like this. These things are what you're smelling, and they're
Okay.
also toxic. So whether you're not smelling it and your cells are dying from it, or you are smelling these other things, the same bad things are happening to you. You're basically
That
killing.
smell that you're smelling is not good to be smelling then.
Yeah, regardless of what's actually doing it, if you're smelling it or not smelling it, it's going to be killing cells in your lungs.
Oh, that's great.
Not really. I don't think that's great.
Sarcastic.
Okay, so this does have its good, right? We talked about this. Did we talk about this? No, I don't think we did. So a couple of people posted the same question from the text about ozone is good far away and bad near. And so the reasoning is what we just talked about. It's toxic to us. It kills things. It tears apart cell membranes. But in the upper atmosphere, sorry, just a sec. This is what the ozone molecule looks like. Actually, I'm going to draw a little lower down. So O3, those three guys are connected together. I didn't draw on the same size because I can't draw. No other reason. So in the high atmosphere, what ends up happening is you have radiation, some ultraviolet radiation, and when it runs into the ozone, this bond breaks, and you end up with an O and an O and an O. But this radiation that can cause cancer has been blocked in the upper atmosphere. Now it can't cause cancer. It's like a sunscreen on the entire planet. And the great thing about the ozone molecule is in the upper atmosphere, remember this O doesn't like to be by itself, right? So then bang, it reforms itself. And then how does that help us? Because then when the next UV molecule or UV radiation comes in, it blocks it again. So it breaks apart when it blocks radiation, and then it comes right back together. And then the radiation breaks it apart and it comes back together. So it's like a self-healing shield for the planet. So as long as it's in the upper atmosphere, it's awesome. If this wasn't in the upper atmosphere, we wouldn't go outside.
Yeah.
We would spend all of our time inside, and when we went outside, we would be completely covered. We'd have goggles on. We wouldn't be able to withstand the UV radiation.
Will it make its way back up into the upper atmosphere?
Ozone that's on the bottom of the earth, down here next to us, no,
In the
it's too,
troposphere? Yeah.
before it ever gets anywhere near going up into the stratosphere, it will react with something in the troposphere, like us or a chair or a curtain or air molecules. It will never get up there. It's too reactive.
All right, guys, I gotta go.
Okay,
Alright.
kind of feel the
Thank you
same.
guys. This was very informative, and I like the visuals. I guess having a visual to things, even if you're just drawing pictures, it definitely gives me a better concept of what it is. I
Okay,
guess it's just my way of learning, so I
sure.
appreciate it.
Yep. I'm
Right.
glad it
Thank
actually
you.
worked this time.
Yeah, seriously.
All right, bye, Sam.
Bye.
That's unless anybody has any other questions, it's probably going to call it for myself as well.
I have a question.
All right, go ahead, Kelly.
For explaining all the pictures and charts in the chapters,
Yeah.
do we just do the figures or do we do the figures and the tables? Or do I have to answer the consider this thing?
No, not to consider this. So, like, I don't know, turn to page 34.
I've been doing like the figures and the tables.
So on page 34, you want to tell me why they put that little table or that little I don't know what to call it, graphic in the upper left-hand corner where it shows carbon, hydrogen, oxygen, nitrogen, sulfur.
Mhm.
And then tell me why there's a picture of a water molecule and carbon dioxide, and then below that, tell me why there's a picture of oxygen, nitrogen, and helium. Why the author would have included those. That's what I'm looking for.
Okay, thank you.
Yep. Anybody else?
I think I'm good.
Okay.
Bye.
See you later. Have a good night. Kill.